calculator for today? There should be some around on the desks. Anybody need one?
By myself. This February. Robin, what is that? That's Christmas. Hey, Christmas cookies? Yes. Yes. Thank you. You're that 10 friends. Then it. Ooh, what was that? Just on 25%.
All right, let's open up to page 296. On Tuesday, we were reviewing our properties of exponents, okay, how we have different manipulations depending on what a certain question might look like, how we can simplify it. And we're going to have to get very familiar with these properties because we're going to use them to our advantage to help simplify exponential equations, solve exponential equations, okay, to help us kind of get an answer in the end. Help me out. Where did we leave off on Tuesday? 7. We have to do it or we finished it? Do it. Okay. So if you take a look at 7 and actually 8, okay, they look very familiar. And they also look very familiar to number 6, which we finished on Tuesday. So let's see how we can tackle these. If you think about, let me zoom out a little bit. If you think about your order of operations, parentheses normally come first. So we got to ask ourselves, can we simplify anything within the parentheses? Can we do 25 divided by 16? Can we simplify those numbers? No, okay? And there's only one a variable in there, so that's already as simplified as it gets. So we tried to simplify inside the parentheses. Turns out we didn't have to. So now we'll move on to exponents. What can we do with this outside exponent? Can we think about a property? If you have a bunch of items being multiplied or divided on the inside, what can we do with that outside power? Maybe look back to 6 from Tuesday. Kind of distribute it in. Okay, so this would be 25 to the negative 3 over 2, 16 to the negative 3 over 2, and then a, we get negative 12 over 2, which would be negative 6. Okay, so we're going to kind of distribute it in to every power. This actually brings up a good question. What if I had x plus 3 to the third? Is that x to the third plus 3 to the third? Do I distribute that power in? It's an outside power.
We got to multiply with 3 by the next.
We got to foil it. Okay. The power of 3 means it's written 3 times. So you'll have to go through a bunch of multiplication and combining like terms, okay? And we probably can anticipate that there would be more stuff involved than just those two items, okay? What's the difference between the way this exponential base and power are written compared to this one? Why can we distribute this power in but not that one? Yeah. Okay, notice how in this example of 7, items are being multiplied together, like the 16 and a to the 4th, or divided. Okay, if you have any type of addition or subtraction, that property of exponents does not work. Okay, you have to use some type of algebra to help you expand it or combine some like terms. Okay, so we have to be careful with that power to a power. If we have that outside power to bring in, we have to make sure that the base is only being multiplied and divided in terms of its pieces. Okay, no addition or subtraction whatsoever. All right, so that kind of clears up the air with that. Where can we go from here? Okay, we brought the exponent in. It's no longer on the outside. Can we use any other properties to help us rewrite it? Because I don't know about you, but right now it looks pretty ugly. Not to judge, but it's ugly. Poor fraction. Can we beautify it? Give it a makeover? Go, Blair.
Right, the 2, it's on the bottom of the fraction, is the square root.
Okay, let's rewrite them as square roots or roots. Maybe we'll do that after we make them positive. You can do that, okay? Notice how we have some negative powers. So by one of our properties, that means we can move the base to the other side of a fraction, and that would then make the power positive. So this 25 is going to move to the bottom, and the 3/2 power is going to be positive, and then the 16 and the a are going to move to the top. Okay, so negative powers, you switch the location. All right, now I like Blair's idea about turning the fractional powers into roots. So for the 16, that'd be the square root of 16 to the 3rd. Okay, the bottom number's the root, the top number is the inside power. And then the same thing for the 25, this would be the square root of 25 to the 3rd. All right, so when we kind of got to this point on Tuesday with number 6, we kind of went over how we can simplify these roots. It actually doesn't matter which exponent or power you use first. You can either cube 16 and then take the square root, or you can square root 16 and then cube your answer. Okay, it doesn't matter. What's up? All right, so would we rather cube 16 or square root 16? Probably square root. Okay, square root of 16 is 4, and then if we cube 4, we'll get 64. All right, for the bottom, we can do the same thing with a 25. You can either cube it first and then square root, or square root and then cube. It doesn't matter. What would we rather do? Yeah? Probably, because I have no idea what 25 cube is off the top of my head. So square root of 25 is 5, and then cube 5. 125. All right, there's our simplified fraction. Do you guys think you can try 8? It's a very similar setup. Okay, maybe use the work we did here as a guide. See how far you can get for that one.
Alright, time to make 3.
Alright, so if I kind of look at the work I did for 7 to help me with 8, I took my outside power and distributed it in to the other powers because everything in the base is being either multiplied or divided together. Okay, there's no addition, there's no subtraction. So that led me here. I then noticed that I have a bunch of negative powers, so I can switch the base, okay, where it's located in the fraction. So that led me here. I then noticed how in the A and the B terms are already pretty simplified, but the numbers have those fractional powers, which means I can rewrite them as roots to help me solve. So I'm curious as to, in the end, what we got as our coefficients out front. I know most of you have a calculator, and if you typed them in, that's fine. But honestly, we should be able to do these in our heads. What's the cubed root of 125? 5, and then square it. 25. Okay. The 8 on the bottom is kind of simple. It actually works either way. We should be able to do it. What's the cubed root of 8? 2, and then square it. 4. How do we do? We got all of it? Some of it? Do we need to talk about any part of it? Amen. Okay, moving on. The next two are kind of similar examples where we're trying to simplify what we get in the end. This time, we're trying to get a single base to a single power. So we're kind of anticipating what our answer should look like in the end. We're not necessarily going to get a fraction anymore like we had in the previous two. All right, so we want a single base to a single power. What do we notice about A? Can we start to rewrite that one at all? Can we use any properties? Any strategy? You see anything, Blair? Yeah. Okay. Why do you want to rewrite the base of 25? It makes both bases the same. Okay, so if we can get the bases to be the same, we are then able to use any property of exponents if we have to. So it would be very strategic, okay, a very good idea for us to get the bases to be the same if we can. Okay, and there are going to be some cases where you can't, and we're going to talk about what we kind of do in that instance. Okay, but try to get the bases to be the same if you can. Don't force it though, because maybe you can't do that. So after rewriting the base of 25 as 5 squared, we are kind of creating a property for us to use. We have that power to a power. So we'll multiply the powers together. We actually have that same property showing up in the other exponential term, another power to a power. So we'll multiply those together. All right, we're getting somewhere, but keep in mind our ultimate goal is to get a single base to a single power. So where can we keep going from here? We're so close. Yeah? There we go. We're going to add the powers, combine the like terms. Notice how we're multiplying the same base. So our property tells us we can add the powers. So 9x and then minus 2. Our single base is 5 and our single power is 9x minus 2. I like it. All right. Let's try B. It looks a little bit more involved. I know, it looks scary. But can we start to maybe think about how we can use some properties? Can we be strategic? it'd be nice if the bases were the same so we could use some properties. Yeah? I like it. Alright, so by rewriting the base of 8 as 2 cubed, you are creating a power to a power property. So we'll multiply those powers. We'll get 6x minus 3. Alright, can we keep going? We are dividing the same base, so what can we do with the powers? Subtract them in which order? Top minus bottom. Okay, so 6x minus 3x is 3x. Negative 3 minus negative 6. It's going to change to a plus 6, so we'll be left with a positive 3. Okay, we're getting there. We're trying to get a single base to a single power. Okay, we do definitely have a single base now. I don't want to have a cubed root there. So what can I do with the root? Two to what power? What do you think, Blair?
Divided, so 3x plus 3.
Over 3. Okay, remember, when we have a fractional power, the top represents the inside power, which this is, and the bottom represents the root, in this case a cubed root. So you can change any type of root to a fractional power. Now if we're dividing this though, we can divide each term separately. So this would be x plus 1. There's our single base to a single power. Alright, so keeping these properties in mind, we're now going to kind of step it up a bit, and instead of just simplifying one exponential piece, we're going to try to do 2. Okay, so looking at the next page, we're going to use these properties to help us solve exponential equations. Notice how we have one exponential on the left and another exponential on the right. And if we want them to be equal, because that's the sign we have in between them, that means we need both pieces to be exactly the same. Okay, that's what equal means. So what we're going to try to do algebraically is actually show that the left and the right are equal. Okay, that we get the same thing on either side. So can we be strategic on how we show that? If we think about some methods that we've used before, okay, notice how the last 2 examples we wanted to get a same base to help us use some properties. Can we do that here? Can we turn 27 and 9 into the same base? Yeah?
27 is 9 squared.
It's not 9 squared.
2/3.
You could do a fractional power, okay? Sometimes a fractional power is going to be difficult for some people to think of, so I suggest maybe thinking of whole numbers. Can you think of a number that you can raise to a power that would give you 27? Yeah? 3 to the 3rd. Okay? Now, if you choose the base of 3 for 27, then you should choose a base of 3 for the 9. 3 to what power would give you 9? 2nd power, okay? Now some of you might be a little bit more apt and noticed how you can use perhaps a fractional power to get the bases to be the same. It'll still work out, okay, when you do the math or the properties correctly, but I would suggest maybe using whole numbers, that way we don't get too confused. Okay, so now that we have the bases the same, let's go ahead and use some properties. We have powers, 2 powers. We'll multiply them through. All right, now can we take a real good look at the equation we have now and think about where can we go from here to help us solve for x? If the left side and the right side are supposed to be equal, aka exactly the same, where can we go from here? Does it kind of make common sense? I'm hoping, yeah?
Just drop this three.
Drop the 3. Don't we already know that the bases match? Right? Isn't that piece already equal? So if we drop the 3, because we already know those are the same, let's go ahead and focus now on the powers. So we're specifically just going to set the powers equal to each other to help us solve for x. Does that make sense? We already know the 3's match, so we don't have to worry about those anymore. Okay, so solving for x, we'll subtract the 3x over, subtract the 10 over, we'll get negative 16. All right, now let's just say, because this is kind of new to us, that you're not quite sure if you solved for x correctly. Okay, you can always check your work if you have a calculator, just to see if the left side is actually the same as the right. So on your calculator, I'm going to go ahead and type in 27 to the, so you have to hit the little caret button. I want to type in negative 16 minus 2, okay, because my x value was negative 16. And my calculator gives me this crazy decimal in scientific notation. Okay, so I know the left-hand side should equal this value. I'm then going to test the right-hand side. So I'm going to type in 9 to the power 2 times negative 16 plus 5. And notice how I get the same thing. Okay, so you're trying to figure out what is the x value that you could plug in that would get both sides to be exactly the same. And you can always check your work. All right, so it looks like we did our algebra correctly. All right, let's try B. It would be wonderful if we can get the bases to be exactly the same. So let's try to think about how can I rewrite 1/4 and how can I rewrite 8. Sometimes one's going to be easier than the other, but once you get one, you can kind of use that to help you get the other one. I think 8 might be a little bit easier for us to initially think of. Can we rewrite 8 as a base to a power? Yeah? 2 to the 3rd. Okay, so if you choose the base of 2 for the number 8, you have to have 2 to some power to represent 1/4. Can we think about what the power should be on this 2 that would give you a 1/4? Yeah? How'd you get that? That's good. There we go. Okay, so we already know that 2 squared is 4, but notice how the number 4 is in the bottom of a fraction, aka it was moved, so it should have had a negative power, okay, because you moved it to an opposite side of a fraction. So since this is a fractional base, it most likely represents a negative power, because you had some type of movement. Okay, so bases are the same, which is perfect. Let's go ahead and use our power to power property. All right, and if we think about it, we want the left and the right to be exactly the same. We already know the bases of 2 are the same, so we essentially just have to check the powers. Okay, when are those equal? So I can add a 2x over, add a 12 over, and looks like divide a 5. So I get 8/5. We doing okay? I'm seeing some head nods, but I'm seeing some yeses too, okay? I'm getting a mixture. We're just going to have more practice. I mean, that's the only way it's going to let it sink in. Okay, the more we do, the more, hopefully, more comfortable we get with it. Let's try C, okay? How can we get the bases to be the same? One's a 2, one's a 4. Any ideas? Can we rewrite 4 perhaps? Yeah. 2 squared. Alright. Notice how both bases are 2. We have a power to a power. So we'll multiply that through. And it looks like on the right hand side we have another power to a power. So we'll multiply that through as well. Alright, any other ideas where we can go from there? Yeah. Square root. Okay, so if we convert a root back to a power, the inside exponent is the top of the power, and then the type of root is the bottom, aka denominator. So if I take 4x minus 14 divided by 2, okay, and divide each number individually, we'll have 2x minus 7. Alright, now, actually some of you might notice, isn't this 2x minus 7 the same power we started with? Yeah, okay. So actually if you took the square root of 4, wouldn't that just lead you to 2? You see how the properties will get you there anyway? Okay, so just in case you don't see those little shortcuts, using the properties will work out regardless. Okay, so the bases match. Let's go ahead and check the powers. I can subtract 2x and add a 3. So I'll get negative 4. Do you guys think you can try 16? I mean, not 16. There's a 16 in it. Do you guys think you can try D, rather? Give it a shot. Try to get the bases to be the same.
Eight squared equals 20. I subtracted for the one, but I added for the other one. That's great. Yeah, I guess it's doesn't matter. Let's try this to
What common base did you decide to use? 2? Okay, so 16 would be 2 to the 4th. 8 would be 2 cubed. And 4 would be 2 squared.
So basically, this exact same thing. I think it was the one oh, right.
I got 9/5. Does that sound right, or did I make a boo-boo? Is that good?
Yeah.
Okay? Be careful. When you do the division, you are subtracting the powers. You have to do 8 minus -3. That's going to change to a plus and you'll get 11. Okay? Be careful with that one. Can we do part of it? All of it? Do we got to talk about any piece of it? It's not bad. Okay, good. All right. Let's try one at the bottom. Consider this one. Solve the equation. Can we get the bases to be the same? I'd say the base of 2 is already pretty simple. Is there some way we can rewrite 1/2 as a base of 2? 2 to what power? Yeah? -1. Okay, it's kind of a fractional base, so is most likely a negative power. Alright, so right hand side, power to a power property, multiply it through. The bases already match, so we just need to check the powers. And solving, looks like we get -2. Okay, so you can check the work. Okay, if you had a calculator, plug it in on the left, plug it in on the right, see if they equal. But I'm curious, okay, because we're essentially solving an equation here. What does this number of -2 represent graphically? If we were to actually get a picture of this equation, what would be special about this value? If it makes the left and the right be exactly the same, yeah? An x-intercept? No. Okay. It's an intersection point, okay? Where if you have the same x value on either side that produces the same y value, aka output, that's an intersection point. Okay? So we're going to check out some intersection points using our calculator. All of these examples that we just did on this page, we were able to figure out the intersection points by hand because we got x equals a number in the end. I need you to do me a favor, and if you look on the next page, look at the equation at the top. The left-hand side has a base of 3. The right-hand side, or sorry, the left-hand side has a base of 2. The right-hand side has a base of 3. Is there a way for us to get those bases to be the same? Probably not, because a base of 2 is already simple and a base of 3 is already simple. Okay, you can't rewrite one to get the other. So unfortunately, we don't have the algebra skills necessary just yet to figure this one out by hand because we can't get the bases to be the same. So this is when we're going to rely on a little bit of technology to help us out, and we're going to graph them to find the intersection point. So on your calculator, let's go to y equals. I'm going to type in maybe the left equation into y1, and I'll type the right equation into y2. Now for the right equation you have to be careful because notice how there's a -1 at the end of the exponential function. So you're going to have to hit the right arrow key to bring the cursor back down from the exponent spot and then type in -1. Okay, you don't want -1 in the power. Before we hit graph, do me a favor and program your window so we can appropriately see the intersection point. I'm being a little nice here. I'm telling you what the window should be. But I'm hoping by now that we're skilled enough to choose a window if we had to. At least play around with it until we can find one that works. Alright, once your window's set, go ahead and hit graph. So there's our first exponential function, and there's the second. Are we familiar, because I know we did it at the beginning of the year, but I'm curious if we kind of remember the buttons we have to press on a calculator to get it to find an intersection point for us. how can we tell the calculator to find it? Yep. Second, trace. That's our go-to menu for basically anything we want to know about a graph. We're going to go down to number 5 because we're trying to find an intersection point. I want you to move the cursor to where you think the intersection point is and hit enter 3 times. 1, 2, 3. Okay, the word intersection should pop up on your screen and you're going to get the exact coordinates of that spot. Okay, so the x solution in this case is negative 3.518, it looks like. Okay, those buttons, okay, that process was kind of highlighted here in the chart on the left-handed side, so you don't have to like write down the steps. It's already there. Yeah. What's another way?
Subtract it over to the left side, put it on the right side, wrap it, and then chase, or do the calculate with 0.
Oh yeah, okay, so instead of doing intersection, Noah wanted to, which side do you want to move over? This one?
Move the left side to the right.
Okay, so if you want to move this exponential to the other side, that means you'd have a 0 on the left. You'll have 3 to the x plus 4 minus 1 minus 2 to the x plus 3. So if this is what you want to type in and it's equal to 0, that means you're looking for x-intercepts as your solutions. So it's just a different graphical characteristic, but it'll give you the same answer. Okay, so it doesn't matter how you want to analyze it as long as you know what to analyze on the graph. All right, now this is going to bring up kind of a big point for us. Sometimes there might be 2 intersection points depending on the way the exponential function looks. For instance, I could have a very quick growing exponential graph, but maybe I have a very shallow one as well. Notice how that can create 2 intersection points. So we just have to be careful to make sure that we have a window available to us, or we think of one, that can show 2 intersection points if there are 2. Okay, but there's probably never ever going to be more than 2. I don't know if that's possible. So it's either no intersection points, 1 intersection point, or 2. Okay, we'll stop there for today because the bell's going to ring in a little bit, but we'll investigate these 3 examples tomorrow on our calculator. Okay, just practice finding those intersection points.